Welcome. In this last lecture we look at the divergence theorem. It's also called Gauss theorem, even so Green was also involved in proving this first. So the theorem deals with solids in space. So let me just draw a solid. Usually I denote it with E. E is a solid, three-dimensional solid. So a three-dimensional region. And important is that such a solid has a boundary. So let's just paint that. That's S. S is the boundary. Surface. It's kind of like the skin, right? So the skin. That's just everything. And it's also oriented. So this comes with an orientation, and the orientation is so that it points outwards. So this is oriented outwards. So if you parameterize that, you have to make sure that RU cross RV points outwards. And now we have also a vector field given. That's an additional thing. F is a vector field. Space. Vector field. So maybe I draw this vector field. This can be arbitrary vector field here. And twirl around. Be arbitrary. It doesn't have to be a gradient field, doesn't have to be the curl of something. It's an arbitrary vector field F. And now we can look at the question, what happens when we look at the flux of the vector field through S? And that's the theorem. So this is the theorem. Divergence theorem tells us that if we compute the flux through S, F ds, this is flux through S, that's equal to a triple integral now over E of the divergence of F dE. That's the last theorem. The last theorem here in 3 dimensions. And actually also the last theorem in this course. So you see the organization of the theorems. We had the fundamental theorem of line integrals in 3 dimensions, Stokes, and Gauss theorem. That's the divergence theorem. So this is 3D, 2D, and 1D. And so it's a divergence theorem because it's associated to the divergence. Stokes' theorem could also be called the curl theorem, and the fundamental theorem of line integral the gradient theorem. So each derivative has a theorem and also an integration. In this case, the integration is the triple integral here. In Stokes' theorem, it was the flux integral. In the fundamental theorem of line integral, it was the line integral. So this is a beautiful theorem. It's a little bit an anticlimax. It's easier to grasp than the Stokes' theorem because it has also some interpretation here. So the interpretation is that whatever leaves the surface is generated inside. So that's it's like a conservation law. So this is what has been leaves the surface, or the solid, is equal to the field generated inside. So the field generated inside, that's this here. So that's the interpretation. Maybe I illustrate it with something. What happens? A special case. Just put that here. is curl of G. So if this is equal to the curl of G, so what do we have then? So then we have on the left hand side, we have the curl of G ds over S. And what happens with this? We know that by Stokes' theorem. By Stokes' theorem, this is the line integral along the boundary, which doesn't exist. So that's equal to 0 because it doesn't have a boundary. And we know also that the triple integral of the divergence of the curl of F, of curl of G, right? That's dv. That's also 0. And it's also 0 because we know that the divergence of the curl is equal to 0. Okay, remember when we used Green's theorem to compute area? Gauss theorem, divergence theorem is nice to compute volume. Let me take an example. So an example would be, we take a sphere. That's also an example where we can compute both sides of the story. And let's just have a sphere of radius 1. And the ball inside, that's E. So E is a ball, a unit ball. S is the unit sphere. It's the boundary. And we can parameterize that as r phi theta. This is sinus phi cosine theta, sinus phi sinus theta, and cosine phi. And actually this is the orientation which also points outwards. So this is oriented outwards. And now let's take a vector field which has divergence 1. So if you look at this vector field, that's maybe the most convenient vector field here. Has divergence it's like 0x in the green case. We have now also a vector field which has divergence 1. And now what happens if we actually do the computation E on the right hand side of the divergence theorem? What's that? So what we get here is just a integral E1, right? 1 dV. And we all know what this is, right? That's the volume. This is the volume. So this is we know that is 4 pi third according to the Archimedes computation. But we can also compute this using the flux. So we can. This is the computation with a triple integral. But there is also a flux computation of this. So what we do is we take this parameterization, and so this is parameterized on r going from 0 to 2 pi and 0 to pi. Of course, that's mapped into the sphere here. And so what we do is we integrate from 0 to 2 pi, integral from 0 to pi. And then we have to take the vector field, which is 0, 0. So that's x, y, z. So that's cosine phi. Here, 0, 0 cosine phi. And dotted with we dot it with r phi cross r theta. Let me just write that down. We have already computed that. That's sinus phi times sinus phi cosine theta, sinus phi sine theta, and cosine phi. Remember, this vector here, this green vector is actually just the length of this vector is just multiplied by sine phi, rho square sine phi in general, but here with the unit circle, unit sphere, it's sine phi. So what we have is kind of just sine square phi here, cosine theta, sine square phi, sine theta, and here we get sine phi cosine phi, and then d phi d theta. So this is by the divergence theorem, this is the same thing. So by the divergence theorem, these two things are the same, but we can compute that. So that's 0 to 2 pi, 0 to pi. And then we have a sine phi, cosine square phi, d phi, d theta. And this is cosine cubed phi. So when we integrate that, that's this integral here. It's just cosine cubed phi minus over 3 from 0 to pi, which is equal to 2 pi third. And when we integrate that constant over from 0 to 2 pi, we get just 2 pi times that. 4 pi third. So we got the same thing. Now you might think that's crazy. You know, that's actually much more complicated than that. Here we had to use spherical coordinates, but already say for an ellipsoid, this is actually still working. And in general, it's very useful. Say in computer science, if you have an object, this is a meteorite here, piece of a meteorite, Campo del Cielo meteorite. It's iron piece, and if you wanted to compute the volume of that, you could chop it off into small pieces and just add up all these small pieces. But it's much easier just to go over the surface. You can kind of get the surface, integrate over the surface, and integrate that vector field here over the surface. That's what the computer can do much quicker. Okay, let's look at a nice problem of a flux computation, which would be quite insane to do directly here. So we have a complicated vector field. We want to compute the flux here, and so oriented. So let's assume oriented outwards. We have always to say that. And I take here inspired by Dali, Salvador Dali, right? So very beautiful, kind of very much math-inspired pictures of this artist. So he kind of imagined. So we have this this two-dimensional version of the cube. You can fold it so that you get the cube. You can fold this together to get the hypercube, a four-dimensional cube. So, but we are not doing that. We are just computing the flux of that vector field through that surface. Now, by the divergence theorem, so the flux computation is complicated. The divergence theorem tells you that we have to compute the divergence of f. Let's compute the divergence of f. So the divergence of f, fortunately, is very easy to compute. You take this, differentiate with respect to x, this with respect to y, this with respect to z, and you add all these up. So in this case, you can see in your head that the answer is 6. So that's 6. And now the theorem tells us that the flux of f ds, that's equal to the triple integral of e, the divergence of f dv. And the divergence was 6, so that's the integral E6 dv. We can take the 6 out, and we get 1 dv, which is 6 times the volume. Now, in this case, we can easily calculate the volume. So there are how many cubes there are. Each cube has volume 1. 1, 2, 3, 4, 5, 6, 7, 8. So that's 6 times 8, that's 48. You have actually lots of such problems also in the homework is a problem like this, and also in the exam, but we never tell you what theorem to use. So you have to have the idea to use the divergence theorem. Okay, I'm not bluffing with my property on the moon. Here is the lunar deed, lunar map. I'm planning to make a lunar park here on my estate, digging here on the other side. You hear it, the dark side of the moon is running here with hot dog stands, and so you can, it's pretty cool, really pretty cool. So let me just close the dark side of the moon here, and so that one can hear me better. And so the problem which I have is what happens with the gravity inside it, radius r of the moon. So when you are here, so this is the whole moon, and now we are in distance, maybe rho, let's call it rho here, in distance rho. What is the gravitational field? So what is the gravitational field? in distance rho from the center. So this is a problem which Newton already has pondered, and so they were interested in this kind of things. But it's quite tough to do it with Newton's law, because you have to integrate over the three-dimensional. So if you are here, you would have to integrate over all masses here going around. You cannot use spherical coordinates to do the computation. But we know the gravitational field is like that, right? It points inwards here. And so F is actually just minus some strength, so F of rho, which is a strength here, and then times a normal vector, which is a unit vector. Now Gauss, who we see here, in the context of the divergence theorem, actually got a very nice description of gravity. So Gauss described gravity with the following law, that the gravitational field satisfies the divergence of F is equal to 4 pi sigma, where sigma is the mass density, and that's the field. So it's a very nice picture, because it shows that gravity is generated by mass. So mass generates, divergence is what field is, generates a field, which is the gravitational field. So that's very convenient, because it allows us to compute gravity also on 10-dimensional spaces, 20-dimensional spaces, any space, curved spaces, whatever you are interested in, you can define this thing. Let's just see what happens here. In this case, when we are in distance, let's call this surface here S rho, and the inside is B rho. So S rho is a sphere, and B rho, this is a ball, both of radius rho. Now, when we compute the flux of the vector field F through that sphere, so the flux through that sphere S rho F ds, this is something you compute in the homework in the case when F of rho is equal to 1. So that's just 4 pi, that's the surface area, rho squared times F of rho. See homework. You do that in the homework in the case when the vector field has length 1 and is perpendicular to the surface. And actually in this case it's negative, right? We have negative here, so this is negative. And what we also know by the divergence theorem, so here comes the divergence theorem. That tells us that is the same thing than if you compute over B rho the divergence of F dV. But now we have this Gauss law. The Gauss law tells us that this is integral of B rho 4 pi sigma. Now we can assume the moon is made of cheese, right? Has density 1, so that's the density. I don't know what it is. Let's assume it's made of cheese, has density 1. So that's actually just 4 pi third rho cubed. Why don't we keep the sigma, just in case it's not, we don't know if it's made of cheese, right? so that's the thing. So now what we have is actually pretty cool relation here. So now this is 4 pi third, and then also with the 4 pi, there's another 4 pi here. Because we have a 4 pi and then the volume is 4 pi third rho cubed. So that's the thing. So we know that this is equal, right? By this identity, we know that this is equal. So this implies, because of that, it implies that F of rho, we have that beautiful law, F of rho, this is the rho cubed cancels with that, the 4 pi cancels with that. F of rho is just 4 pi third sigma. Pretty cool. So that's a pretty cool computation, and So it shows that the gravitational field is actually linearly growing. It grows with rho. So at the center there's zero gravitational field, it grows linearly. So if I let people down here with on the other side, this is actually like a harmonic oscillator. It just bounces fastest here, becomes slower here. Now it also allows us to, outside the moon, so if rho is bigger than the radius of the moon, what happens is the same computation works. And then what we have is we have f of rho, and you see what actually happens is that this part here is just 4 pi times the mass, 4 pi times the mass, and this is also 4 pi. So we divide by rho square, so this is actually just mass over rho square. So this is Newton's law. So Gauss law is implying Newton's law. And the advantage of it, we could also do it in 4 dimensions and get it in 4 dimensions. In 4 dimensions it would be over rho cubed.